stacks. Once we really ask a question, what is done, do a bit of experiment, make small pictures, things fall in place. So, we have seen all of it, except that we have not seen how to process Gimple statements. That is the only thing that is to be seen. Once we see that, you will be able to write your own passes and manipulate Gimple. So, let us look at that. So, the slides say manipulating Gimple and RTL IRs, but we are going to skip RTL IRs. The material was there, so I thought might as well include it in the slides. Those of you who are interested can read it up later. Okay. So, an overview of Gimple. Using Gimple APIs, we will talk about adding Gimple pass and internal view of RTL, manipulating RTL. This is the overall plan. We will not cover all of it. Some of it has been covered, some of it will be excluded. So, an overview of Gimple. So, it is essentially a language independent 3 address code representation. Computations are represented as sequence of basic operations. By now, you know what it means, because you have seen the textual representation. You understand what Gimple is. Control constructs are explicated into conditional and unconditional jumps, and we have had a lot of discussion on do while loops and for loops, etc. So, by now you know what this means. I do not really have to emphasize. Previously, the only common IR was RTL, register transfer language. The drawbacks of RTL for performing high level optimizations was it was too close to the machine. There were too many details. For example, stack, offsets in the stack, etc. We do not need them for high level optimizations. Why not abstract syntax tree? ASTs are more structural. The control flow of the program is not evident in the abstract syntax tree. In the abstract syntax tree, we will say here is a while node and this is a statement. So, the fact that this gets executed again and again, I have to interpret the while node. Okay. And if I have a nested while loop, I will say within this there is a while node. It would be useful to get a single thread of flow in the program, control flow in the program. I need a control flow graph. Abstract syntax tree is not a suitable. There is some optimization that can be done at abstract syntax tree level, but not all of them. Particularly those with involved flow of data and uses of data items will not work well with abstract syntax tree. There have been attempts of doing data flow analysis on trees. They have not been very successful, they have not been very popular. Okay. So, generic is something that is essentially a union of all possible abstract syntax tree, because we are assuming that we may have C++, we may have C, and we get ASTs. Obviously, AST nodes for C would be different from C++, they may have some different AST nodes, etc., etc. So, therefore, a common AST set of ASTs was called generic, and generic is converted into Gimple. So, Gimple is essentially an outcome of this work for a simple IR on the work done at McGill University. They first defined an IR and called it simple, then they extended it to Java, so they called it Gimple with a J. So, GNU folks picked it up and they converted J to G, G for GNU, and that is why it is called Gimple. Okay. So, let me skip. So, earlier Gimple involved trees, and that is the reason why you keep hearing tree name everywhere, fdump, tree all, etc. But now there are no trees anymore. Why did we have trees? Because AST had trees in them. Okay. So, now we have tuples. Essentially, it is a tuple representation of Gimple. It is a vector of various values. Okay, tuples contain following information: the type of the statement, the result, the operator, the operands, etc., etc. Okay. So, this is the output that we get f with fdump tree all, and this is the output that we get with fdump tree all raw. Okay. So, this is a tuple, this is x is equal to 10. So, this is integer constant x 10 null. This is how the fields are organized in a tuple. Okay. So, when you get raw details, you actually see Gimple as tuples. Yeah.
Why is it called a variable declaration in that assignment?
Beg your pardon? Here?
Second but the last line.
Why is it called variable declaration? Can someone say why it is called variable declaration? Can someone guess what it could mean?
variables are involved.
That might be a global variable.
It might be a global variable. It basically introduces a new variable declaration because it creates an artificial a dot 0 is created for it, right? Okay. So you can even represent control flow like this. So you can see how it looks like. Let me not go over too many details. I have just shown you how to find out what the raw field is, what raw does. You can look at the declarations, appropriate declarations in the C file and figure out the various fields of the structure. Let me rush over this. This is the main point that I want to come to. Manipulating Gimple representation, accessing Gimple representation. So a basic block, in order to iterate over Gimple statements. So Gimple statements are a part of basic block. Now what is the structure? So at the top level we have a call graph. Every node in the call graph represents a function or a procedure. A procedure in turn represented by a control flow graph. A control flow graph in turn is a collection of basic blocks. A basic block is in turn a collection of Gimple statements. Okay. So if a basic block is a doubly linked list of Gimple statements, you can go to the previous statement, you can go to the next statement. Okay, these statements are represented as Gimple tuples, and you can process the statement through iterators. So there are well defined APIs that let you iterate over Gimple statements. Okay, so you have this iterator. So let's say you have this declaration called basic block BB and this Gimple statement iterator GSI. This is a variable name, this is a type, and I can say for each BB. Okay, so this lets me iterate over all basic blocks in the control flow graph. So I pick up a basic block, and then for a basic block now I want to iterate over all Gimple statements. So I pick up GSI. So I say GSI is equal to GSI start BB. This API gives me the first statement of the BB, and until I end up reaching the last statement, or I have finished the end, I have reached the end, I say, so this is like a for loop. So you have GSI next is equal to AND GSI. So give me, so it iterates over the list, and then I say, let's say find pointer assignment. So I call my function with this as a parameter, and now I can look at it this as a Gimple statement and I can process it. So this is the basic block iterator, this is the Gimple statement iterator, get the statement, first statement, true if end is reached, advance iterator to the next Gimple statement and return the current statement. Okay. Now I can extract parts of the Gimple. What do I need? I may want to find out what is LHS, I may want to find out what is RHS, I may want to find out what is the first operand on the RHS, what is the second operand on the RHS. So you can see the names are quite intuitive. RHS1, RHS2, RHS code, it gives me the operator on the RHS. Okay, and a complete list can be found in file gimple.h. There are many other APIs which you can directly use. You really don't have to use the structure pointers. Okay. So we will look at some sample examples in order to discover more information. Let us see how we can discover local variables, how we can discover global variables. All this will be a part of the code that is given to you in resources for the lab assignments. And I will show you one example of how to discover pointers in statements and how to write a pass for discovering assignment statements involving pointers. Okay. And what do I mean by assignment statements involving pointers? Either the RHS is a pointer or the LHS is a pointer. Of course, if LHS is a pointer, RHS better be a pointer. I mean, you can't have a non-pointer assignment being made to a pointer unless you want to change the type structure. Okay, the first two are relevant to your lab assignment. The last two basically combine everything and let you see a big picture by putting the whole things together. That is the motivation behind what we are going to look at now in the remaining 25 minutes that we have before we break for lunch. So how do I discover local variables in Gimple IR? I write a function void gather local variables, okay, and I say list cfun local variables. Which function am I talking about, by the way? Which procedure am I talking about? Whose local variables is it finding? This is what comes from the context. Okay. So, there is a context, a current function being compiled. This is a global variable that is maintained. Okay. How do I get that global variable? So, I can say push cfun, pop cfun, we will see those examples also later. But there is a notion of a current function which is held in this variable called cfun. Okay. So, I can say this is the list of the variables of the current function. I can get the name of the current function as well. If I do not have dump file, if it is not been opened, I do not want to print it, I simply return. Otherwise, for each local declaration, this is the iterator on the local variables. So, I can go over the list of local variables of this particular function, and I say if it is not an artificial variable, because I want to collect only the variables that appear in the source. There are many variables that GCC creates, SSA variables, variables for global variables, for global source variables, variables that are temporary variables with d something, etc. So, I want to exclude all of them. So, if it is not an artificial variable, then I am interested in it, then I simply print it. I say get name of the list, it is a pointer tree node that holds the variable, and it will find the name of the variable, and then I advance it to the list. That is how I can discover local variables of a function. As you can see, it is pretty simple. Once you start looking at the brass tacks, doing these low level things is very easy. How do I get global variables? Well, it is much the same way. I have a function that gets global variables. I have something called varpool nodes. This is a global variable. As soon as I set the context for a function, this global variables gets set. So, I get the list of global variables, and I say I put a for loop, and I put a for loop, I get a node here, and I say go to the node next, and until I keep getting a non null pointer at the end, this node arrow next will be null. So, for loop will terminate, and then I once again exclude artificial variables, I once again get name, and I print the global variables. Go to the next item in the list. In the afternoon in the lab session, you are going to take this code, you are going to invoke this code with minus FLTO, without minus FLTO, with minus FLTO partition equal to none, and you will see how the same program behaves differently. That is the idea. So, I want to find out assignment statements involving pointers. So, I have this main program, pretty meaningless program, but it has some pointer statements, and this is what is its Gimple representation. So, the blue statements are the ones that I would like to identify. I would want to write a pass in GCC that will give me identify the blue statements. So, I have to first find out what are the pointers in the Gimple representation. So, I write these functions. So, I say this is pointer type is a function that we have written below, and is pointer variable. So, I get a variable, a tree node of a variable, and I say if it is a pointer type, return true. Okay. And how do I determine pointer type? So, if pointer type p for this type, so there are type names associated with it. This is a macro pointer type p. You can use cscope and see the actual definitions. Okay, return true. Otherwise, if it is an array type and various things. So, you basically look at the type information and determine whether it is a pointer type. Okay. So, how do I write the main function that finds pointer assignments? So, this is given a statement, I am trying to categorize that statement whether it is a statement that involves pointers or not. That is the thing that I wish to do. So, is Gimple assignment statement? If it is not an assignment statement, I want to exclude it. I want to find out assignment statements involving pointers. I am not want to find out conditional statements involving pointers. Maybe I can have something in the else part to do something, you can figure it out how to do it. But I ask this question, is Gimple assigned? This is standard API, tells you whether a particular GSI particular statement is an assignment statement or not. You can figure out how does it do it. It will extract RHS code, it will check whether it is Gimple assigned. If yes, it will return true, otherwise it will return false. So, I figure out whether something is an assignment statement, and then I get LHS, I get RHS 1, I get RHS 2 operands, and check if either of them can be pointers. So, I have already written the functions that tell me whether it is a pointer. So, I first check that the nodes that I get are non null, because I may not have RHS 2 for example. Okay. So, I check if it is true, if it is non null, is it a pointer, or is this a pointer, or is this a pointer. If any of these is true, then I know that this is a pointer statement, and I can call this function called print Gimple statement in the dump file, and I simply pass the statement, it will print it, it will print it properly in the textual representation, and I increment the number of pointer statements that I found. Okay. The dumps that you have been seeing are produced by statements such as these print Gimple statement. There is an internal data structure of Gimple as a collection of tuples. There is a function which would traverse it and will print it and give you a textual dump, so that you can examine what is happening with your program. So, extract the LHS of the assignment statement, extract the first operand, extract the second operand, print the Gimple statement, and that is it. Now, how do I put it together? So, I write my execute function of the pass. We have already talked about how to hook up a pass. We have to create a pass variable, Gimple opt pass, then we will have a get function, then we will have execute function. This is the name of the execute function that we have. Okay. What will it do? It has a basic block, it has GSI, it will initialize variable count. So, maybe for local global variables everything is initialized to 0, and then for each BB in this function, and now I have shown another iterator. Now, I say the cfun is what has the current function context. For each basic block, for each GSI of the basic block, I call that function find pointer assignment statements, and I simply print the variable count, and that is my pass. That will classify statements that involve function pointers. Okay. Now, current function Gimple statement iterator. So, if I run it on it, we find that for main it shows that there is one statement, assignment statement involving pointer. For call me function it shows 2, does not show 3. It does not show 3, because this is treated like an array, a memory location. This is not seen as a pointer assignment statement, although in the original code, if you see the program that we had submitted, this was a star of p plus 3. Okay, but because you are doing it as p plus 3, address computation is happening. So, it's the resulting address is not treated like a memory, like a pointer at this stage. One could argue over why it is not done so and so on, but let's ignore it for the time being. How do we make it an interprocedural pass? So, that is also not very hard. So, now I have again same function in some same way. I will declare my function, I will get my call graph, okay. I will have basic block, I will have GSI, I will initialize var count, and now I say for node equal to C graph nodes. Okay. So, now I am iterating over the call graph, I am picking up a particular function in the call graph. So, I take a node and what do I do? So, C graph nodes is essentially the variable that stores the call graph. Okay. And then I say push cfun. This is the way of setting the context, because for every node I want to know what is the var pool count, I want to extract the local variables, I want to know number of statements, number of basic blocks, all these are global variables. I want them to be initialized for every function. So, what I do is I call this API called C function, and this node is the node in C graph, its declarations, I pick up that field and I basically call this API. Essentially, I am setting up the context. Okay, you can go through the details, look at these APIs, and there are lots of details, structure, member of the structure and other structure, but it is a matter of detail, it can be figured out. The whole idea is I am setting up the context here. Okay. So, which means that the remaining code, in the remaining code, whenever I refer to Cfun, I am going to get this function, maybe f1, next time it is f2, Cfun will refer to f2. This is the code that we already know. For each bb in the current function, iterate over the Gimple statements, find pointer assignments, and then you just pop the function. Now, you are done with the context. Okay, say that my variables do not hold these values anymore, and this is in a for loop, you go over and push the C function. So, you can see that once you write intra-procedural analysis, at least couching it as a simple inter-procedural analysis that works on functions independently is very easy. All that you do is take that function body, put it in a for loop which iterates over the call graph, and make sure that you set the context.
We are not iterating the call graph in a particular order.
Good question. That is one question in your assignment. Here we are simply picking up the nodes. It is useful if you really want to do proper inter-procedural analysis that is flow and context sensitive. You can't begin anywhere arbitrarily. You will have to begin with main. So, there is one function, there is one assignment in the afternoon which says identify which function, identify whether there is a main function in your translation unit. It is something that requires you to find out callers of the main function. For all other functions, we are saying print me callees of the main function. So, it is useful to be able to distinguish between a main function in the call graph, and once you have main function in the call graph, you can find out its callers, you can find out its callees. That is what you will do in the assignment in the afternoon. Yeah. Yes, nothing else. Number of pointer statements is 3 in this case. Observation: information can be collected for all functions in a pass, and better scope for optimization. Of course, if you really want to do proper inter-procedural analysis, you won't simply say node equal to C graph node and node equal to next. You will pick up node, first identify main function, and then you will say for this main function give me the callees, and then you will iterate over the list of callees. For each of them, maybe you will go to their callees and so on. So, this is where we would like to stop now, but I will be happy to take questions.
Yeah. So, when iterating call graph, GCC does not provide any way of marking the node, saying that this is visited, this is not visited.
Good question. This was one of the assignments that we had planned for you, where we wanted you to print a call chain, and we said it would be a recursive function, it would be a recursive program. So, our TAs did the assignment, and all of them unanimously told me, please remove this, we are not giving people, participants, enough time to do this. Unfortunately, because there is no direct way of remembering that I have already processed this node. It also does not make sense, because you want to control, so the order in which functions are processed. So, GCC, I believe, takes the view that it is your responsibility, and this is what we had done. So, this was an assignment in my course, and we thought we will simplify it and push it in this workshop, but a week ago when the TAs did it, they came back and said we took 3 hours to do it, and at the end of 3 hours we are still getting some segmentation fault somewhere, and there is some problems, so let us remove it. If there was some such thing, then I would have really pushed this assignment in the workshop. Yeah.
You had, if we are looking for proper inter-procedural analysis, then on real applications, will it be a heavy thing?
Yes, I am glad you brought up this issue. So, his question is, if you want to do proper inter-procedural analysis, and by proper, I guess I know what he means. He means that apart from the call graph, we can load the entire function bodies and correlate function bodies together. there is one issue of how big the size of the program could be in the memory, but assuming we have a large memory, the concern is that you want to correlate information across functions, and in the interprocedural analysis situation we get paths that are not possible. So, in the afternoon we will talk about it. There is a notion of a context sensitive analysis. So, we would like to collect information from a procedure in possible calling contexts. Now, this number of calling contexts could be very large, and therefore, in general flow and context insensitive analysis is considered very inefficient. There is a classical method by Sharir and Newelly, which is the most precise method, called call strings method, published in 1981. They give a method whereby we can perform precise interprocedural analysis, but unfortunately the number of contexts is very large. In general, in the presence of recursion, the number of, so context is essentially stack snapshots. How many different stack snapshots can you have? That is a context, that is a calling context. In presence of recursion, you can very easily imagine that the number of contexts is unbounded, okay, infinite, if you assume that you can go to any recursion depth. Fortunately, because we have finite variables in the programs, unless you involve integers, if you are only doing analysis of variables, these problems, because of the finite values, the problem is still decidable even in the presence of infinite contexts. The problem remains decidable, but it still is intractable. It's exponential, it takes exponential time. So, no compiler uses Sharir-Newelly method, because it requires you to construct millions of contexts at a given program point. This is a problem that we started investigating about a decade ago, and we said this is not fine, the method is very nice, let us make it work. So, now that we have a few minutes, let me give you in a minute or two a gist of the work that I mentioned that gave us great speed ups. So, what we essentially did was, let me not say what we did, or maybe I should. So, what we essentially did was, if you have so many contexts, let us find out which one of them are relevant and which one of them are not relevant. And by asking this simple question, essentially the same algorithm became very efficient. So, when we implemented this in GCC 4.0.2 in 2007 and 8, we figured out that for towers of Hanoi problem, the original Sharir and Newelly method would take something like 4,000 seconds. Towers of Hanoi problem, it's a bad case of recursion. That is a good test of how good an algorithm could be. With this new method developed by my PhD student Bhageshri, we were able to process the same thing in 2.96 milliseconds. The original method required more than a million call strings, we required 38 call strings. This still does not work for pointer analysis. So, we were able to show that this method can really work. For bit vector frameworks, we found out it was very efficient. But my dream has been, and I have been looking at it for about a decade, my dream has been to process a million lines of code and do precise pointer analysis in less than 10 minutes. That is the benchmark that I have set for myself. For a decade we have been looking at it. So, first roadblock was we did not have efficient interprocedural analysis. Now, we had an efficient interprocedural analysis, it still does not scale to pointers. So, then we did something else, and I am going to present the core idea today, and there will be an assignment based on it on the last day. So, we did something, and now it appears that the goal is reachable. We are not there yet, but it seems that we can still, again the idea is to find out what is relevant and what is not relevant. It seems to give us very interesting results. We will talk about the results in the afternoon, and you will do an assignment, look at the concept later. Still we are not done, because we are still unable to create a precise call graph. We still have to load all the function bodies. So, until we are able to take care of all these things, the most interesting thing that we have learned in past, and this is what I consider as a takeaway from this research, most people introduce approximations in order to achieve efficiency. They say in order to do precise context sensitive analysis, I have to remember all these contexts, and the number of contexts is very large, and therefore let me merge all the contexts, let me build approximations. What we have discovered is, if you try to create approximations for efficiency, you can actually make it inefficient. Okay, I mean, unfortunately I can't explain it in one sentence, but those who are interested, talk to Swati or talk to me later. We will be able to give you n number of examples where by introducing an approximation, apparently because of efficiency, there are situations where you make it inefficient. On the other hand, if you were to model precision properly, if you were to come up with a theoretical concept which captures exactly what you want, so you do precise analysis, it can actually be faster than imprecise analysis that people actually use for efficiency. So, our pointer analysis, for example, is faster than GCC's pointer analysis. GCC does a flow and context insensitive analysis because it is believed that flow and context sensitive analysis is very, very inefficient. So, they do insensitive analysis for efficiency. Our flow and context sensitive analysis is faster than GCC's pointer analysis, and the reason is very simple. Because of approximation, you compute this world of information. We simply asked a question, do you need all of it? And when you try to model it carefully, we discover actually only this much of it is required. So, because of approximation, you keep increasing the world of values, you compute lots of values. And if we do precise analysis and we say I need only this much, then I compute only this much, so I can be faster. That is the intuition. And yet we are not there because we still have to work out on very efficient APIs. Our method is still not scalable. So, that 1,000,000 lines of goal is still far away. Maybe we are a couple of years away from it, or maybe 3 years away from it, we do not know yet. So far we have been able to scale it to 30,000 lines, and maybe in a few months we will be able to go to maybe 100,000 lines if we use better APIs. Will we reach 1,000,000 lines in 10 minutes? I really do not know, but that I am willing to wait. I have been looking at it for a decade. I do not mind waiting for another decade if I can solve this problem, because the entire world believes that this cannot be done. I believe it can be done, and we would like to try it. Maybe it can be done, maybe it cannot be done, but it is a worthwhile exercise trying to ask hard questions. If there are no other questions, we will stop here. If some of you are interested in knowing about the research activities that we are doing, talk to my students, talk to me. They should be able to give you a fair idea. Not everyone may know everything because some of them are new, so they will point you to the right person to talk